All right, so let's start from the very beginning. So today we will start talking about the magnetism, right? We started discussing it in our recitation classes, but we need to bring everyone to the common denominator, so I will repeat it to some extent. So, um, guys, okay, right. So you remember from the world of electricity, if you have a point charge, right, it produces electric field, and it doesn't matter what happens to this charge. If it's stationary, it produces the electric field. If it's moving, or if it moves, it also produces the electric field, right? So, but people noticed that if you have a moving charge, right, back then in old days, if you have a moving charge, that then there are some additional phenomena around this moving charge which couldn't be explained by the presence of the electric field. So those were the evidences of the presence of the different field. Okay, they call it magnetic field, right, and started investigating, right. So the bottom line, in order to produce the magnetic field, a charge must move. So moving charge, only moving charge can produce magnetic field. So and everything is in the magnetic world is sort of like in dynamics. In order to produce magnetic field, a charge must move. Then in a few classes, when we will discuss magnetic force, again, in order for a charge to experience magnetic force, again, the charge must move. So everything is in dynamics in the world of magnetism. So only a moving charge can produce magnetic field. If a charge is stationary, no magnetic field around. God created nature this way, right? We're just trying to describe it, model it, right? Okay, so as a result, we can identify three systems which can produce, which produce magnetic field. So first, of course, a moving charge, and it produces magnetic field. Second, of course, bunch of identical charges drifting in the same direction. What is that? Of course, it is current. Current will also produce magnetic field. And the last system, permanent magnet, right? So it also produces magnetic field. But of course, a logical question. So since the basic system which produces magnetic field is a moving charge, so every time it's a moving charge, right? So where are the moving charges in our permanent magnet, right? So there must be somewhere moving charges. And the answer is quite simple. If you recall classical model of an atom, right? So we have a nucleus at the center, and then we have electrons orbiting that nucleus. Orbiting, it means traveling, moving. So there are moving charges. As a result, under certain conditions, they can give us a non-zero magnetic field. But of course, under certain conditions, because only certain types of materials can show a non-zero magnetic field. But of course, that's for high-level classes, right, to discuss which materials and so on. Right, so we're going to discuss these three systems, but this permanent magnet, most of the time we're going to use to discuss some stuff conceptually, right? For these two systems, book offers mathematical expressions, like formulas, which can be used to calculate. And I used to follow the book, right? I used to introduce the expression for this moving charge also. But what book offers expression for this system is not completely correct. And our theoreticians in the department, they kept telling me, right, so we shouldn't be using this, right? But I tried to follow the book, right? So eventually, yeah, I caved, and we're not going to use an expression which book offers to describe this system, because this is the process of magnetic field production of this system is much more complicated, right? So as a result, we're going to describe sort of using formulas, right? Mostly this system, current, right? So anyway, so now let's grab just a permanent magnet and introduce some basic ideas, some conventions which we need to live in the world of magnetism. My brain is still switching from the electricity to magnetism. It will take maybe one class. Okay, so permanent magnet. And of course, so if somebody gives you a permanent magnet, and of course we all know that it has two poles, right? South and north. We'll discuss those poles in a few minutes, right? So what can we observe if we start playing with the permanent magnet? Observations are trivial. You all know them. If you try to bring two like poles together, you will feel that they repel, right? So like poles repel. Right? And of course, if you flip one of the poles, right? So if you try to bring opposite poles, of course, they attract. It's sort of like a positive and negative charges, right? So opposite charges attract, like charges repel. Very similar idea. Okay, so now there are south and north pole, right? And you have a permanent magnet, right? So what is natural response of anyone who starts playing with the permanent magnet for the first time? So if you have south pole and north pole, can I crack it and get separately south pole separately from the north pole? Completely normal desire to try, normal desire to do that, right? So if you try to cut the permanent magnet into two pieces, right? I don't know, to your disappointment, or maybe you will be, I know, glad to get two full magnets. So you're not going to get a south pole separately from the north. You will just get two magnets. Okay, two magnets more better than one, for example, right? So maybe it's a bad luck. You can try one more time, cut these two smaller magnets into a smaller one, and again you will end up now with four full magnets: south north, south north, south north, right? So it doesn't matter how many times you're going to try to cut into pieces, you will never get the monopole. You will never get south pole separately and north pole separately. Right. Okay. So the monopoles, magnetic monopoles, there are no magnetic monopoles. But it doesn't mean that it's impossible for them to exist in the universe. No one has proven theoretically that it's impossible for magnetic monopoles to exist in the universe, right? But so far, no one has ever observed a single monopole. So if you manage to find a magnetic monopole, the Nobel Prize, it's huge, the Nobel Prize immediately yours next year. You don't have to wait for 40 years until you're old to get the Nobel Prize for whatever for something you've done when you were in your 20s or 30s. So immediately, Nobel Prize is yours. It will be huge, right? So as a result, since no one has observed, have seen, right, any magnetic monopole, so all the equations, all the theories were developed, right, and all the equations were written, assuming that there are no magnetic monopoles. But again, it doesn't mean that it's impossible for them to exist. Okay, but do we have electric monopoles? Of course we do, right? Electric monopoles, yes, do exist. Positive point charge, it's electric monopole. Negative point charge, it's an electric monopole. So it's kind of unfair. We have electric monopoles, but there are no magnetic monopoles. I don't know, maybe God forgot to create magnetic monopoles, right? But it's probably the only place, okay, maybe there are more places, right, where there is where the electric world and the magnetic world, where the similarity is broken, where similarities are broken. So we have electric monopoles, there are no magnetic monopoles. But still some people, some researchers try to find magnetic monopoles, right? And if you watched that sitcom, The Big Bang Theory, right? You remember in one of the episodes, Sheldon got a NSF grant to go to the pole in a search for a magnetic monopole, right? And you remember how happy he was when he thought that he found magnetic monopole, because immediately Nobel Prize would be yours, right? And how he was crushed when he realized that all the data was just a piece of nonsense, right? Because he was too annoying. Right? So again, my point is there are no magnetic monopoles. But again, it doesn't mean that it's impossible for them to exist in the universe. Okay, so enough about magnetic monopoles. Now we know that a magnetic field exists, right? There are some. Okay, I cannot follow your chat, right? So now we know that magnetic field exist, right? And so how can we, now we need to introduce some conventions, right? And so first, how can we detect magnetic field? Basically, the question is detect or probe, right? So the question is, which system can be used as a probe system? And the ideas are very similar to the ideas which we use to introduce the electric field, right? So you remember we also introduced the probe system in the to detect electric field. We use the small positive probe charge. So similar ideas must be used here. So first of all, our probe system must be small so that we would not disturb the magnetic field of the system. Magnetic field of the system. Magnetic field of the system. So then, of course, your probe must be sensitive to the presence of the magnetic field. So what can that be? A small permanent magnet. A small permanent magnet can be used as a probe system. Where do we usually have a small magnet? Fridge magnet's still too big, right, and too inconvenient. Compass needle. Compass needle, small, right? Plus it can rotate, showing us the right directions, right? So compass needle can be used as a probe system. It's small, right, and it's sensitive to the presence of the magnetic field. Okay, so now it's a permanent magnet, right? Compass needle. So how should we call the sides of the compass needle, right? We know that one side is the north pole of the needle, the other one is the south pole. So we need to come up with a convention. We need to come up with a convention and label the poles of the needle. So in order to introduce this convention, let's recall the Earth. Let's use the Earth. Of course, it's spinning around this axis of rotation, right? Of course, this is our north geographical pole, right? So that is the north geographical pole. And here, of course, we have the south geographical pole. And now, so how do we, people, use compass? In old days, and still some people use it now, we use it to find a direction to the north geographical pole, just to orient ourselves, right? So every time we use compass needle to find the direction to the north geographical pole. Then, of course, it makes sense to simplify our life, right? So to label and call that side of the needle which points to the north geographical pole as the north pole of the needle. So right now, this convention has not much to do with physics, or maybe nothing to do with physics, right? It's just a convenience. So, and that's the convention. So basically, that side of the needle which points to the north geographical pole is called the north pole of the needle, of this compass needle. So that is north. This is then south, right? And west east, it's for orientation, right? Okay, so that's the convention. And now, of course, we also know that the Earth is the basically permanent magnet, right? Permanent magnet. So let me, for example, draw it as this rectangle, right? Instead of sphere. Okay, let's imagine that there is a rectangular permanent magnet inserted in the Earth, right? So now, following this convention, how should we call this side of this permanent magnet of the Earth and this side? Right? So, of course, we remember observations. Opposite poles, okay, opposite poles attract. So if this pole of this magnet, of this needle, if this pole is attracted to that pole of the Earth, it means that this is the south magnetic pole. So since this is north, then this is the south magnetic pole. So we have, and of course, this side, the opposite side of this permanent magnet is the north magnetic pole. So you see, we have two sets of poles, geographical poles, and then flipped magnetic poles. So now, whenever you hear the word pole, you have to be careful and clarify which pole is being used, right? Geographical pole or magnetic pole, right? Because they are flipped. Then, also these magnetic poles, they're slightly displaced from the geographical poles. And moreover, they drift. They constantly drift. It's like a couple of years ago, I remember I watched one of the episodes of that BBC show, Top Gear, right? Maybe some of you know that. And in 2008, I think by car, they traveled to the pole. And I was impressed. I thought, oh, they probably traveled to this point, right, to the north geographical pole. But then when I started reading, right, actually, no, they didn't travel to the north geographical pole. They traveled to the point where the south magnetic pole was in 1996. So now all these travelers to the pole, they most of the time they travel to the point where the south magnetic pole was in 1996. And even in Wikipedia, there's a long list of these people visited the pole. But again, most of the time they just travel to the to that point, which is in Canadian territory, and so the distance between that point where it was in 1996 and current position of the south magnetic pole is a few hundred miles away. So it's like in 24 years that south magnetic pole has drifted by a few hundred miles, right? So those poles drift, right? And who knows, maybe in a million years they will even flipped. Who knows? All right, what happens inside of the Earth? But again, the bottom line, they drift. And they're slightly displaced from the north, from the geographical poles. Okay, then, so that's what I just told you, right? And the last piece, which is important, the north pole of the needle gives us a direction of the magnetic field. So in this case, you see north pole points that way, north pole of the needle, so it means the magnetic field points that way. If the north pole of the needle points that way, so that will be direction of the magnetic field. So on this slide, there are three major points, and I highlighted them. So compass needle is our probe system. Then that's the convention why we call this side is north and that side is south of the compasses, right? Of permanent magnets. And the north side of the compass needle shows the direction of the magnetic field. Again, somebody's mic is on, right? No, right now I cannot find this. It's too deep, right? Because we have like 100 students, right? Okay, all right. So And now, in order to complete this picture, to make it look nicer, right? So let me also draw magnetic field lines, which we haven't introduced yet, but if, we're about to start introducing magnetic field lines. So, and let me add these lines to make this picture look better. Right, so, and now let's introduce these magnetic field lines. Again, the same story, lots of similarities between the world of electricity and the world of magnetism. And lots of similarities in terms of these electric and magnetic field lines. Again, magnetic field is invisible, right? So it's good to come up with idea how we can visualize. So we can draw some lines and see where a magnetic field is stronger, where it is weaker, and to see directions of the magnetic field, right? And so how can we draw those magnetic field lines? We just basically need to map the field. Now we have a probe system, grab your compass needle, right? So let's say you have a permanent magnet and start moving your compass needle and getting the magnetic fields. Right? So you pole gives you direction of the magnetic field, right? And North Pole gives you direction of the magnetic field. Keep moving your compass needle everywhere, right? Getting magnetic fields. And, all right, so let's say after some efforts, you will end up, and then of course you need to connect those vectors in order to get magnetic field lines. So here is an example of magnetic field lines created by a permanent magnet. North Pole, you see, and the South Pole. Right? So first of all, it looks like as if magnetic field lines started at the North Pole. You see, they started, right? And then they would go and end at the South Pole, it looks like. Because magnetic field lines all the time form closed loop. And they're getting close to the magnet. You see these tons of dashed lines? Those dashed lines closing these magnetic field lines. Why we don't have why do they form closed loops? Why don't we have some beginnings of these lines and endings? Because it's a consequence of the fact that there are no magnetic monopoles. In the world of electricity, we had monopoles, right? Positive charges and negative charges. As a result, all the time, our electric field lines started on positive charges and ended on negative charges, because all the time they started on monopoles. Now we don't have monopoles. Because of that fact, since we don't have monopoles, as a result, all magnetic field lines form closed loops. So if you manage to get some open loop, there are two options. Either it's just a mistake, you are wrong, right? Or you deserve a Nobel Prize that you found magnetic monopole, right? But most likely, but still, my Nobel Prize still possible. Right? Right. Okay, so because there are no magnetic monopoles, all the time magnetic field lines form closed loops. But again, it looks like as if North Pole behaved like a positive charge and South like a negative charge, and you see it looks like magnetic field line starts on the North Pole and go into the South Pole. But of course, they get closed using these lines which go through the magnet, a permanent magnet. So how can we get, for example, now information about the magnetic field, because these are magnetic field lines. The same idea like we used to analyze electric field lines. So magnetic field is tangent to the magnetic field line. And again, I position also here the compass needle, right? So you see again, the North Pole of the compass needle gives us the direction of the magnetic field. And the magnetic field is tangent to the magnetic field line. Then if we position it here, again, tangent. Position it here, again, tangent, right? Again, the same story, very similar. Magnetic field is tangent to the magnetic field lines. Magnetic field strength, the same idea. So here, for example, we have density of lines, density of magnetic field lines is larger, so of course magnetic field is stronger. Here, density of lines is smaller, magnetic field is weaker. Right. Okay, so this is just a demonstration, which, yeah, when we were at school, I would bring some plate with kind of small compass needles in order to demonstrate it. But now uh, it's locked up there, and I don't have it here in my apartment, of course. Now, so we introduced all the conventions, basic ideas which we need in order to work in the world of magnetism. And now we're about to start introducing expressions. All right, and before we start introducing expressions, we need to refresh two important ideas which you already used in Physics 1. First of all, now we're going to deal most of the time with systems which will have vectors pointing in three different directions. For example, like up, this way, and that way. Three mutually perpendicular vectors. And of course, if you try to draw those vectors on a piece of paper, on a whiteboard, of course, every time one of the vectors will be sticking either out or in. So let's refresh convention about how can we draw those vectors. So first of all, if a vector or current points into the board or into the page, we're going to use crosses. Or for example, a current, right? So you see we have a circle and a cross in the middle. What's the? It's like an arrow flying away from you. If an arrow flies away from you, what are you going to see? You're going to see stabilizers forming the cross. And I like this picture, so I put this cat reading the book World Domination for Cats. All right, and opposite situation, what if vectors is out, or a vector is out of the page, out of the screen? In that case, we're going to use dots. Or current out of the page, again, it will be a dot with a circle, right? This is the same idea. If an arrow flies towards you, right, so it's written bad karma, right? Then of course, what are you going to see? You're going to see a sharp dot and the edges of the arrow, right? So that's what you're going to see. So we're going to use them from this day almost till the end of the semester, all these conventions, almost every class. Then cross product. So from now on, most of the equations which we're going to introduce are going to have cross product. And again, you used cross product in Physics 1. You remember when you discussed torque, angular momentum. So now we need this mathematical tool in this course as well. So what is this? Vector or cross product? So it's just basically mathematical tool which was introduced by mathematicians in order to describe what we observe around us in the world, right? So, for example, let's say we want to take a cross product, find the cross product between these two vectors, A and B. So as inputs, we have two vectors, and as an output, we have a vector, vector C. So if you want to find magnitude of vector C, of course, you just need to take magnitude of A, magnitude of B, times sine of a correct angle between these two vectors. You remember how can we find the correct angle? And the angle less than 180 degrees is the correct angle, right? We'll refresh that. So that's how you can find magnitude. Direction, in order to find a direction, we need to use the right-hand rule. I usually call it number 1 because there is another right-hand rule which we introduced in our recitation classes, right? So, so first of all, before I start refreshing right-hand rule, you need to remember that vector C, the direction of the vector C is perpendicular to both of these vectors. Perpendicular to both of these vectors. Guys, I see you, I don't know what's happening in the chat, but if you're trying to ask me some questions in the chat, no, I don't think that I will be able to read also chat and lecture it. So no, switching, I don't think that it will work. But if you
there's a lot of mic feedback.
My feedback. Why you didn't tell me?
I'm not sure if it's rubbing against your t-shirt or what.
Yeah,
No,
it
it
could be where.
never happened before. Um, okay, so you know what? Let me switch to a different mic then. You don't have to chat. Just tell me. Okay, I will test what is happening um, after the class with a friend. Okay, let me switch this way. Okay, is it better?
Now you're like quiet.
Quiet. Okay.
Your voice sounds distant
Is
that
this
way.
better? Is this better? No?
Not
It
really.
just
No.
sounds really quiet now.
Now it's like kind of like an echo.
Damn it. What's changed?
That sounds good.
It's better?
Oh, now it's worse again. But for a second, it was okay.
Better? No? 1, 2, 3.
So quiet.
But was it like this in the previous lectures?
No.
No?
No.
Huh. What has changed? I didn't change anything in the system. Let me change this. Okay.
It just sounds like the mic is rubbing on something.
Right, I'd go back to the same mic, Andre. Just move it, tighten it up.
Okay. What do you mean by to the same mic?
The one you were initially using.
Yeah, I switched back to the initial mic.
Okay, it seems reasonable now.
Reasonable.
It,
Is it better? Hello?
A little, yeah.
It's still a little quiet, but it's definitely better. We can continue.
Yeah,
I think it's good
let's do
enough.
it. Let's do it.
Yeah, I agree.
Okay, sorry guys. Right, so something unexpected. I will call an expert after the class, right, for help. Okay, let me save these changes. Okay, I can take a shirt off. Is it rubbing? Okay. Okay, I will just try to speak louder then. Right? Maybe it will help. And also keep my head down towards the mic. Okay, so the direction of vector C must be perpendicular to both of these vectors. That's basically how this tool was introduced. So they don't try to find the logic, why is it perpendicular? Just in order to describe what we observe around us, we need to introduce this tool. And mathematicians did introduce it. Right? So then how can we find direction? Because it can be perpendicular to vectors A and B, up or down. So now, right-hand rule. The way the book presents what? Okay, so the way the book presents the right-hand rule. So first, take the first vector in the cross product and align your arm or your hand along that vector. First vector. It's a very important order of vectors. Never flip them. So take the first vector and align your hand along that vector. But of course, when you align it, you can align it like this, like that, like this, like that. So then, the next step, second step, you need to orient your hand. So orient, I mean like rotating. You need to orient your hand in such a way so that you can bend your fingers in the direction of the second vector in the cross product. So in this case, in the case which is shown in the picture, right? So first, vector A that way, so I have to align my hand like this, you see? Then, if I position it like this, you see, I cannot naturally bend my fingers. I will need somebody's help to break my fingers, right? or like this again. I cannot bend my fingers towards vector B, which is somewhat towards us, towards you. So I have to position my hand like this, and then only in this position I can bend my fingers towards you, which is direction of vector B. And then my outstretched thumb gives me the direction of C, up. All right. So it's one way. Again, first align your hand along the first vector in the cross product, A. Then orient it so that you can naturally bend your fingers towards the second vector. And your outstretched thumb gives you direction. So you see my actually hand matches this hand on the picture, right? Up. So that's the direction of C. There's also a rule where you can use 3 fingers. Nothing wrong with that, it just looks funny. Right, so that's why I don't use it. All right. But again, it works great. Right? So this finger, use it for A. Align it along the vector A. Then these 3 fingers, align them along the vector B, you see. Or 1, but I use 3. And then your outstretched thumb gives you direction of the C. So in this case here, you can apply it. Right? So this is along A, these fingers towards you along B, and C is given, direction of C is given by my thumb. So it's exactly the same. Okay, the same rule applied direct. Okay. 2 different, whatever you prefer. They basically give you the same results. Right? Some people like this, some people like that. Right? So pick one and use whatever you feel like doing. Using. I usually use this. Some students use that. Right, so that's the right hand rule, and guys, right? So we're going to practice, but not much in our recitation classes, and make sure that by the so that make sure that you are quite comfortable using this right hand rule, because from this point, from this moment, we're going to use right hand rule almost every class. And it's kind of funny to see the final exam of physics 2, because students are sitting in the classrooms, right, and turning and twisting their hands, right, if you don't know what they do. But they just are trying to apply right hand rule. Okay, so a couple of examples. Let's look at a couple of examples, right? So for example, let's say we want to find the cross product of A and B. So what do we have to do? We need to, how should I position myself? Right? Okay, so, no. Again, it's a problem because I'm looking at the screen, which is flipped. Okay, so I need to position first, align my hand along vector A. All right.
Professor, we can't hear you anymore.
Hello? Hello?
You mute. Okay.
There we go. Now it's good.
You know what? Maybe my shirt covers it. Okay, let me change my wardrobe. Okay.
It
so,
sounds like a connection there.
connection.
Yeah, check the connection on either end.
Yeah, it could be a loose wire.
Maybe. I've been using this mic for already quite some time. Maybe that's the issue. Okay, so I cannot. Okay, does it work now? Is it working?
Yeah, it's good.
Okay, so I try to move myself as little as possible. Right, and then I think I have the second spare. I will change it. I need to find it. All right, so I have to orient my hand like this along the first vector in the cross product. And right now, even orientation is correct, because now I can naturally bend my fingers along vector B towards the second vector, right? And as a result, my thumb, you see, my thumb is into the screen, into the board, right? So that's direction and of course into the board, it means that we have to use that convention, we have to use that cross. Then this, for example, situation, vector A and B. Again, the order is very important. So first find the first vector in the cross product A, right? And align your right hand, right? Sorry, left-handed people, right, guys? Feels like a discrimination, but right? You can see physics. So A cross B. Again, so first align your hand along the first vector, right? Like this. But again, you need to orient it so that you can naturally bend your fingers towards the second vector. So I have to position my hand like this. And only then I can bend my fingers towards the second vector in the cross product. And my thumb, you see my thumb, in this case is out. So in this case, the cross product direction of vector C is out. Out of the page, out of the board. Okay, so practice it a little bit, right? Okay, not a little bit, practice it. If you still struggle, come to office hours, and it's very simple mechanical rule, right? We can practice it. Office hours today actually it will be from 2 to 3, and Thursday also from 2 to 3. So then, okay, Biot-Savart law. And it's one of the fundamental laws which cannot be derived. It's as fundamental as Newton's law, Gauss's law, Coulomb's law, right? It was written based on observations. So it's basically give us an expression which can be used to find magnetic field created by a wire with a current. Any wire, it doesn't have to be straight. Over here, they still show the straight wire, but it can be bent, twisted, whatever, right? As long as you have current. So let's assume that we have this wire with the current I, you see that's direction, and let's say we want to find a magnetic field at this point, completely arbitrary point. So first of all, we need to take infinitesimally small section of the wire. And the formula will be for the contribution to the net magnetic field created by this section, only by this section, of length delta S or ds. I don't know why book uses delta, I would probably use ds. Right? And ds is presented, you see, as a vector. It is presented as a vector. Vector, direction of this vector is determined by the direction of the current. In the wire, we have only one direction, direction of the current. So current, direction of the current defines direction of this ds. Then we also need to know a direction to the point where we want to find magnetic field. That's why we need to introduce r hat. Whenever you see a hat, it means it's a unit vector. It means it's a unit vector. Magnitude of 1. All right, because very often I see on the exams, students try to find the magnitude of r hat. It's just 1. Okay, and then as a result, we can basically, again, as I said, it cannot be derived. We just need to say, I can say, so here is the Biot-Savart law. Right. So it's a contribution to the net magnetic field created by this small section. If you want to find, for example, magnetic field created by the whole wire, then of course you need to integrate. You need to add all the contributions from this ds, then from the next ds, and then from the next ds, and so on, until you cover the whole piece of wire. So in this case, so for contribution from this section, mu naught, new constant, permeability of free space. Basically, what's the meaning of this mu naught? Similar to the meaning of epsilon naught in the world of electricity. Basically, it gives us, it allows us to, it describes magnetic properties of the vacuum. Epsilon naught, electric properties of a vacuum. Divided by 4 pi, and then the value of the current, and then cross product. That's why I had to refresh the cross product. So cross product of ds and this unit vector r. So magnitude of this, it will be ds times r hat times sine of angle between them, direction, right-hand rule, and divided by the square of the distance between this section ds and the point in question. So we're going to practice this law in this form in the next recitation class. There is a nice problem with two semicircles, right, and the small straight sections, right, which is a little bit lengthy, and of course integration is required, but integration is not that bad. So we're going to practice the formula next class, next recitation class. And yeah, no derivations, right. Yeah, what is also important, yeah, direction of the magnetic field. There is no component of the magnetic field along the current. Well, like you can apply right-hand rule to find direction of B. So delta S that way, right? So I have to position my hand like this along the delta S, right? And then I have to orient my hand so that I can bend my fingers towards vector R, right? Because that is the second vector in the cross product. You see this R. So I have to position my hand like this, so I can bend my fingers along R, and you see my thumb is along sort of to some extent towards you, this direction B. Right? ds cross R, and thumb gives me this direction B. From now on, we're going to use cross product almost every class. Units of B. Okay, the value of the constant mu naught, right? We already started using in our recitation classes. Right? Then units of magnetic field, Tesla. It's named, of course, after this great guy, Nikola Tesla. But now, sorry, Dr. Mittler, right? But I hope, guys, you still remember that Tesla, it's a name. It's not just the name of the car, it's the name of this great guy. But you know what, like a year ago, I decided, okay, just Google Tesla. Pressed. And then it took me 10 search pages before I found the link to the first website about Nikola Tesla. All those tons of links before, it's all about the Tesla car. It's so unfair. Okay, so I hope the next generation of students will still remember that Tesla is the name of the guy, not the name of the car. Okay, so then just to feel to get a feeling of the magnetic field strength, right? On the surface of the Earth, 10 to the power of minus 5 Tesla. So kind of small, right? Okay, can you hear me still? Because again, I see some chats popping up.
Yeah, you're fine.
Okay, good. All right. Then a fridge magnet, 10 to the power what, minus 3? Yeah. Superconducting magnet. It's one of the strongest magnets, right? Only 10 Tesla. So 1 Tesla is a very, very large magnetic field. Then, of course, that Biot-Savart law, BS law, right, abbreviated, can be used, of course, to find magnetic field created by infinitely long straight wire. Infinitely long straight wire. Of course, it can be integrated, right? Of course, it can be integrated. We're not going to do it. Let me just hold you for extra minute. Because in a class, we're going to introduce Ampere law, and this formula, which I'm going to present, right, can be found much, much easier. Because the integration, to integrate Biot-Savart law, it's kind of complicated, right? It would take me, for example, 15 minutes of integration. So no. Right, so let's assume that we have a straight piece of wire with current I infinitely long, and we want to find magnetic field at this point. So basically, you just need to grab Biot-Savart law, integrate it from this infinity to that infinity. So if you do that, if you do integrate this expression, you will end up with this. Mu naught times I divided by 2 pi d. What is d? D, it's the shortest distance between the point in question and the wire, right? So we're going to use this formula also a lot, and usually students don't have any troubles using that formula. So then, That's how you can find the absolute value of the magnetic field at this point. But of course, magnetic field is a vector. What about direction? So direction, of course, you can find, for example, using compass needle, right? Compass needle map the magnetic field, right? And if you do that, you will notice, okay, you will see that magnetic field lines form circles around the wire, circles. And of course, the north pole of the compass needle can give you direction of the magnetic field and direction of the magnetic field lines. But of course, we don't have the compass needles all the time with us. So we need to come up with some rule, right? And usually we have right hands with us all the time, right? So we can use a right hand rule to find direction of the magnetic field lines. Again, but you need to remember that they form circles, right? So circles around the wire with current. And the right hand rule, outstretch your thumb in the direction of the current, and then curl your fingers, outstretch your thumb in the direction of the current, and curl your fingers around the wire. Direction of your fingers is going to give you direction of the magnetic field lines in this case. Right? So right hand rule number 2, I usually call it, right? Because right hand rule number 1, that's what we use to find direction of the cross product. And this is basically right hand rule number 2. Okay, and if you look from the bottom at this picture, you will see this current going away from you and magnetic field lines. They form circles. And again, find direction of these circles, right hand rule number 2. Okay, so let's call it a day. All right, can you hear me now still well?
Yes.
Okay.
Yeah.
Okay. So yeah, I need to test it and probably change the mic. Right? I don't know what's happening. Since I've been using this mic almost every day for the last, soon it will be a year. So probably maybe there are some problems with wires. Some loose. They're getting loose. Okay, guys. So if you have questions, you can ask. Right. Otherwise, I will see some of you tomorrow and some of you on Thursday. Again, sorry for these technical issues, but it's completely unexpected.